In this video, we'll see the fundamental theorem of Markov chains and look at a few examples of using it. The fundamental theorem of Markov chains says the following. Suppose that x0, x1, x2, ... is a Markov chain, so that the state space is finite, the chain is irreducible, and the chain is aperiodic. We saw the definitions of irreducible and aperiodic in the previous video. Then, the theorem says, there exists a unique stationary distribution, pi, so that the following holds. First, for any two states I not equal to j, the limit, as t goes to infinity, of the probability that x sub t is equal to I, conditioned on having started at x sub 0 in state j, is equal to pi sub I. That is, the probability of I under this distribution. The second conclusion is that for any state I, pi sub I is equal to 1 over the expected number of steps it takes to return to state I, having started in state I. That is, this is the minimum t, so that x sub t is equal to I, conditioned on having started in state I. We're not going to prove this theorem in this class, but we will be using it, so we should understand it. To break this down, we're going to first take a closer look at the conclusions, and then we'll take a closer look at the assumptions. So let's start with the conclusions. The first conclusion, or sort of the zeroth conclusion, is that there exists a unique stationary distribution pi for this Markov chain. Recall from the previous video that a stationary distribution pi is one that satisfies pi times p is equal to pi, where p is the transition matrix. So here's the example that we saw in the previous video. What this conclusion says is that since this Markov chain happens to be irreducible and aperiodic and has a finite state space, this stationary distribution is the only stationary distribution. The theorem also guarantees that such a stationary distribution exists, even in other examples that we haven't seen before. The second conclusion says that for all I not equal to j, the limit, as t goes to infinity, of this probability, this is the probability that at the tth step we are in state I, given that we started at state j, that this probability as t goes to infinity is going to tend towards pi sub I. In other words, after a long enough time, the probability that we are in state I approaches pi I. And importantly, this holds no matter where we started. This holds for all j. To see this in action, let's return to this example. So I coded this up, and I computed the probability of being in any given state at any given time from various different starting distributions or starting states. So for example here, we started with the uniform distribution. This red line is the probability that we're in state A at any given time. The blue line is the probability that we're in state B, and the green line is the probability that we're in state C. So at the beginning, we have 1/3 probability of being in all of the states, and then as time goes on, these things change. For example, after the first step, it's much more likely that we're in state A than we are in either states B or C. And you can see that by about the 8th step, things have kind of leveled out, and the probability that we're in state A is about 4/7, the probability that we're in state B is about 2/7, and the probability that we're in state C is about 1/7. That's not a coincidence, that happens to be the stationary distribution. And we can see that the same thing happens no matter what distribution that we start in. So for example, here's the distribution where I start at A with probability 1. Something different happens at the beginning of the chain, but by the end of the chain, or at least after 8 time steps or so, it looks basically the same. And same story if we start at B. So the fundamental theorem of Markov chains says that this isn't just going to happen for this example, it's going to happen for any aperiodic, irreducible Markov chain with a finite state space. The third conclusion of the theorem is that for any state I, pi sub I, the probability of I under the stationary distribution, inversely proportional to the expected number of steps it takes to return to state I. That's what this quantity here is. To see this in action, let's again look at this example. I coded it up, and I just looked at the empirical probability of returning to a given state in some number of time steps. So these graphs come from like 1,000 trials or something like that. So we can see that if we start in state A, with probability about a half, we're going to return to state A in one time step. That makes sense. In fact, it's exactly a half. With probability a quarter, we'll return to A after 2 time steps. That's what happens if we do this. And with probability a quarter, we'll return to A after 3 time steps. That's what happens if we do this. And there is no way in this little Markov chain to return to A in more than 3 time steps. We're always going to get there in 1, 2, or 3 time steps. What this conclusion says is that the mean of this distribution, the expected number of steps it takes to return to I, is going to be inversely proportional to pi I. In this case, pi sub A is 4/7, so that says that the mean of this should be something like 7/4. Seems about right. Similarly, I did the same exercise starting from B. You can see it's a little more spread out there. And the theorem says that the mean of that distribution should be like 7/2, which is maybe there-ish. And finally, we can do the same thing if we start from C. And the theorem says that the mean of this distribution should be like 7. So something like this. Once again, seems plausible. Okay, so that's pretty cool. It says that not only do we approach the stationary distribution in the limit, but we can just read off from the stationary distribution the expected amount of time it takes to return to any given state. So those were the conclusions of the theorem. What about these assumptions? In order to understand these 3 assumptions, let's quickly go through what happens when each of them fails to hold in turn. Our first assumption is that the state space is finite. It makes sense to ask what happens if the state space is infinite. But let's say the Markov chain is still aperiodic and irreducible. If that's the case, then something similar to the fundamental theorem of Markov chains holds. Either there's going to be a stationary distribution with this property that we said before, or something else can happen, which is that the probability of ending up at state I, having started at some state j, is always going to be 0. So this is not something that would happen for the finite state space. It's a good exercise to try to come up with examples of Markov chains on infinite state spaces where both of these things occur. Our second assumption is that the Markov chain was irreducible. Once again, we can ask what happens if this is not the case. For example, with this Markov chain here. This is a not irreducible Markov chain. In this case, we can decompose the Markov chain into irreducible components. These correspond to the strongly connected components of the underlying graph. So in this case, those would be like this. Now, with probability 1, the chain is eventually going to get stuck in one of these components. In this case, it'll get stuck in one of these 2 components here. These are the only ones that have no outgoing edges. By the fundamental theorem of Markov chains, each of these components, assuming they're aperiodic, are going to have their own stationary distributions. Thus, the Markov chain will eventually end up converging to one of these 2 stationary distributions. However, which stationary distribution the Markov chain ends up in depends on what happens in the earlier part of the chain. For example, if I started at state E, then I'm definitely going to end up here. I'll never end up over there. But if I started in state G, there's some probability that I end up here or over there. The third assumption that we made is that the chain is aperiodic. Once again, it's natural to ask what would happen if this were not the case. That is, if the chain were finite and irreducible, but periodic. Here's a simple example of that down here. This is kind of a silly Markov chain. It's just deterministic. It just sort of goes in a circle. In this case, it turns out that there's still a unique stationary distribution pi. In this example, it's just the uniform distribution 1/3, 1/3, 1/3. And in fact, we still have that pi sub I is inversely proportional to the expected amount of time it takes to get back to any given state. For example, here it takes 3 steps to get back to A, and the stationary distribution places weight 1/3 on A, so that checks out. However, the difference between this situation and the conclusions of the fundamental theorem of Markov chains is that it may no longer be the case that the chain converges to the stationary distribution. For example, in this little example here, we can look at the sequence of these probabilities, say the probability that x sub t is equal to A, given that x sub 0 are equal to A, let's say. We can look at this sequence over all t. Well, this is going to be, for t equals 0, we'll get 1, the probability that we are in state A at time 0, having started in state A, that's just 1. But for t equals 1, we'll get 0, because the probability that we're going to be in state A at time 1 is 0. We'll always be in state B. And similarly, at t equals 2, the probability that we're in state A is 0, because we're always going to be in state C. So that's 0, 0. But at time step 3, once again, with probability 1, we'll be in state A, and this will repeat. In particular, this sequence does not converge to a limit, so it definitely doesn't converge to pi sub I. So that wraps up our discussion of the assumptions and the conclusions of the fundamental theorem of Markov chains. Now that we understand the statement of the theorem, let's see a couple of examples of how we might use it. The fundamental theorem of Markov chains guarantees that there exists a unique stationary distribution, and this can be pretty powerful. In particular, it makes it pretty easy to find the stationary distribution. If we can just guess pi and show that pi times p is equal to pi, then we know that pi is the unique stationary distribution. Here's one application of that idea. Suppose that x0, x1, ... is an irreducible aperiodic Markov chain with a finite state space. The proposition says that if the transitions are symmetric, meaning that the probability of going from j to I is the same as the probability of going from I to j, then the stationary distribution is going to be uniform on all of the states. Let's see a quick proof. Suppose that pi is the uniform distribution on the states of the Markov chain, and let's call that collection of states capital S. And let P be the transition matrix. To show that pi is the unique stationary distribution, we just need to show that pi times p is equal to itself. So let's compute pi times p. So this is equal to some vector, and the ith component of this vector is equal to the sum over j of pi sub j times p sub ji, which by the definition of pi sub j is just 1 over the size of s. So this is 1 over the size of s times the sum over j of p sub ji. But by our assumption of symmetry, this is 1 over the size of s times the sum over j of p sub ij. And now this thing is equal to 1, because this is just the probability that starting from state I end up somewhere, some other state, which always happens. So then this whole thing is equal to 1 divided by s. So that means that this distribution, pi times p, is again the uniform distribution, aka it's just equal to pi. Therefore, pi times p is equal to pi, therefore pi is the unique stationary distribution. Hooray! To see an example of where we might want to use a proposition like this, consider the following shuffling procedure on a deck of cards. So we're going to repeatedly do the following. Let's choose 2 cards independently at random with replacement. And then we'll just swap them. So that is, I'm just going to pick 2 different cards randomly and swap them. And if I happen to pick the same card twice, I'm not going to do anything at all. We can observe that this forms an aperiodic irreducible Markov chain with a finite state space. Indeed, x sub t is just going to be the order of the deck after we do this procedure up here t times. This Markov chain is aperiodic since there exist self-loops. In particular, if I choose the same card twice, I'm not going to do anything. And it's irreducible because you can get to any ordering of the n cards by successively swapping things. The state space is just all of the possible orderings on n cards, which is finite. Thus, we can apply the previous proposition to this Markov chain and conclude that the stationary distribution is uniform. In particular, this means that as t goes to infinity, the distribution on orderings of the cards goes to uniform. Or in other words, that this is a legitimate shuffling procedure. If you do this for long enough, you'll end up with a uniformly shuffled deck of cards. It might take you a while, though. This next proposition is another application of the idea that in order to establish that something is a stationary distribution, you just need to show that pi times p is equal to itself. This proposition is about random walks on graphs. So let x0, x1, and so on be a random walk on a connected, undirected, non-bipartite graph, G. That is, my state space is just the vertices of V, and if xt minus 1 is equal to V, then xt is going to be a uniformly random neighbor of that vertex. So if I have some graph, this will just give me some walk around that graph. Then I claim that there's a unique stationary distribution pi, and moreover, that distribution pi looks like the following. Pi sub v, the probability of any particular vertex v, is just equal to the degree of v divided by 2 times the number of edges in the graph. This is interesting since the probability of being in state v, pi sub b, only depends on the degree of v. It doesn't depend on anything else that's going on in the graph. Let's prove this proposition. First, pause the video and convince yourself that this is a legitimate distribution. That is, that these things sum to 1 when you sum over all the vertices of V. Now that you're convinced of that, let's prove that it's a stationary distribution. So once again, all we need to show is that pi times p is equal to pi. So here's p, which is our transition matrix. So now the u-vth entry of p, this is going to be equal to 1 over the degree of u, if uv is an edge in the graph, and it'll be equal to 0 otherwise. Thus we can compute this product. The vth entry in this product is equal to the sum over u of p uv times pi u. Plugging in the definition of pi u up here, and also our characterization of p down here. This is the sum over all u, such that uv is an edge in the graph, of 1 divided by the degree of u, times the degree of u, divided by 2 times the number of edges. Conveniently, these degrees cancel, so this is the sum over u, such that uv is in E, of 1 divided by 2 times the number of edges. There are the degree of v, many things in this sum, so this is just equal to the degree of v, divided by 2 times the number of edges. But conveniently, that's just pi sub v. So therefore, we conclude that pi times p is equal to pi. Thus, pi is the unique stationary distribution. Here we should also check that the underlying Markov chain is aperiodic and irreducible. It's irreducible because the graph is connected. And to see that it's aperiodic, we can use the fact that it's a non-bipartite graph, which is also undirected. In a little bit more detail, the fact that it's non-bipartite means that there's an odd cycle somewhere in the graph. And the fact that it's undirected means that there's a path of length 2 in the graph. Just go across one edge and go back where you came from. And those two things together are enough to show that the underlying Markov chain is aperiodic. Okay, so that's about it for this video. To recap, we saw the fundamental theorem of Markov chains, which says that an aperiodic, irreducible Markov chain with a finite state space has a unique stationary distribution pi. Moreover, pi tells us a couple of things. First, the probability of being in a state I as t tends to infinity is going to tend to pi I no matter where you started from. Second, from this distribution pi I, we can read off the expected amount of time it takes to return to a state I. We also saw a few examples showing that this was pretty powerful. In particular, to identify a stationary distribution, it suffices to guess the stationary distribution and just verify that pi times p is equal to pi. We'll see further applications of Markov chains and the fundamental theorem of Markov chains in future videos. Thanks for watching.